Hello everyone. Now in this video we will study about design of a gearbox, the chapter of design of mechanical systems. Now what are the learning objectives of this chapter? Now as per our university guidelines, the main objective of this chapter is to prepare layout of machine tool gearbox and select number of teeth on each gear. Now in numerical we will see in detail that what is the meaning of it, but this is just a theory part, so we will discuss here theory only. Now first we will see about introduction to gearbox. Now what is gearbox? Now as we know, gearbox is a mechanical device which is used to transfer power. Now technically with the power it has few more functions. Now what are those functions? Now if you check for importance of a gearbox, you will come to know that it has two important features. Those are, number one, it has speed variation. Now we can vary the speed with the help of a gearbox. Similarly, we can vary the torque transmission with the variation. Now if we'll take the example of a two-wheeler or four-wheeler, we'll come to know that it has multiple gears. It has reverse gear in case of four-wheeler, and we have first gear, second gear, third gear, fourth gear, and etc. Now the thing is, as you will change the gear, you will get more speed. Now in case of first gear, the speed is lesser one, but the torque is greater. Now in case of second gear, the speed you will get it more than the first one, but torque will be reduced. Now if we'll go with this, you'll come to know at the highest speed of a gear, you will get lesser torque. So that is why whenever we require higher speed, at that time we use higher gear, and whenever we require lesser speed and more torque, we will go with the lesser gear. Now similarly we have reverse gears also. After this, how we can determine, or how do we determine this variable speed range? Now there are few progressions in our syllabus. Through those progressions we can decide which should be selected. Now there are four progressions, as you can see here. First one is arithmetic progression, geometric progression, logarithmic progression, and harmonic progression. Now what is meaning of it? Now through these progressions we can determine that what should be the speed to the first gear, what should be the speed to the second one, third one, and more than that. But out of all these four types, we use geometric progressions. Now what are the reasons to choose this geometric progression? Now there are three main reasons through which or because of which we use geometric progression. Number one, if we select geometric progression, first one, there is a constant loss of economy cutting speed in the whole RPM range. Now suppose the gearbox is having range of 10 RPM to 1000 RPM. Now in that, while making the gears, there is a cutting speed, or there is a speed which cuts the gear while manufacturing. The thing is, there is a constant loss of it. Now we'll see in detail again. Second one, there is a constant loss of productivity in the whole RPM range. And the third one, it's a better design features. Now, how do we determine this constant loss? Now, whatever we have seen three reasons before, we will check out the same reasons over here. First one, the optimum cutting speed for material should be maintained by every cut, for every cut. Now while manufacturing a gear, the optimum speed, the minimum speed, or the suitable cutting speed should be maintained for every cut. Now the thing is, while cutting this, as the diameter is reduced in each cut, the speed has to increase. And due to this stepped regulation drive, the RPM values are provided such that for one cut, all the others cut will not be operated at the optimum cutting speed. Now this is, we are talking about a stepped regulation drive. Now in that, if we get this point, it tells you that for one cut, if you are using 10 rpm, and then for the next cut, it will be automatically not operated at 10 rpm, means the same speed will not be maintained. Now what will happen then? They will operate at a lower cutting speed. So this difference between two cutting speed, there is a difference between these two cutting speeds. So that is why, to avoid this, we use geometric progression. Now what it exactly shows? Now as there is a formula here we have formula nx plus 1 divided by nx, where this x is lower one and x plus 1, it's the next speed that we have it. So here through these things we can get a geometric progression ratio. Similarly, loss can be seen here through these values. The loss is equal to geometric progression ratio, that is phi x minus 1 divided by phi x plus 1 into optimum velocity. Now through this point we can maintain the constant loss of economic cutting speed instead of just random variation. Next, second reason is that the constant loss of productivity in the whole RPM range. Now the thing is, the productivity of machining operation is defined as the surface area of metal removed in time. Now while manufacturing a gear, that disc should be cut by a particular device, and that machining operation is done on it to remove the material, and that removal of surface area is the productivity of machining operation. Now in case of a stepped drive, only one cut will be given, the maximum only one cut will give optimum machining of the workpiece, and during all other cuts until the changeover there will be loss of productivity. Now if we'll check this point and the last point, we'll come to know both are exactly similar. We are talking about step drives. Means what? In the first step or in the first speed, whatever the cut will be given to it, it will not the same one to the other speeds. So to make that constant loss, we use this geometric progression. Now here the third reason, the better design features. Now to optimize the dimension of a gearbox, the proper material selection for each of the gears as well as the provision of multi-speed or multi-stage arrangements are most essential. Now we know while designing the gearbox, there is a limit of space, there is limit of speeds. Now there is a constant supply of engine speed, and there are certain outputs that we need it at gear 1, 2, 3, 4 and all. So that is why there should be a proper material selection, and also as we are getting with multi-speeds and multi-stage arrangement, there should be a proper dimension of a gearbox which is easily suitable in case of two-wheeler or four-wheeler, whatever machine we are doing it. Now the thing is, it is difficult to establish the gear ratio in multi-speed arrangements. So it is therefore suggested to select the ratio and the number of stages to meet the requirement by trial and error. Now this is the important point, as it is difficult to establish the gear ratio in case of multi-speeds arrangement. So therefore here in this case, it's trial and error method. With the help of trial and error method, we can check for number of stages and we can check for the ratio. So this is the problem with the better design feature. Now this difficulty we can easily overcome by geometric progression ratio. Now there are two things in this. Number one, in case of geometric progression with the progression ratio, every x value is also in the geometric progression with ratio of phi x. Now this we will better understand with the example, which is next one. Now the progression ratio multiplied with the constant value also gives value with the geometric progression with each value constant times greater. Now for understanding these 2 points, we will get it a little bit better. Now how we can write example of a geometric progression. If we'll get with this, you'll come to know that here nx plus 1 is equal to nx into phi, where this phi is geometric progression ratio, where nx plus 1, suppose nx is first speed, x is equal to 1, then x is equal to, if you are taking x is equal to 1, then nx is the first speed n1 and nx plus 1 is the second speed. Now if we check it simply, that n2 is equal to 5 times of n1. It's a simple ratio. So that is why, because of this, the geometric progression is much more suitable in case of a gear design. Now this is the formula we have seen. We'll check for the example. Now for the example, there is a table and there is a speed range in it. Now the speed starts with n1 is equal to 30 and it ends with n12 is equal to 375. Now the thing is, if we check for these values, so these all values are same, it is 1.26, means what? The progression ratio is constant. So this we have to understand over here, that n1, n2, if we relate it, so simply n2 is equal to n1 into this phi. Now if we'll simply multiply this 30 with 1.26, if you will simply multiply this 30 with 1.26, you will get this 37.5. So it is simple multiple. So this is the feature of a geometric progression ratio, and that is why we use it. Next we have structural diagram, which is a part of this chapter. Now in case of a structural diagram, how do we write it? Now first we will understand its formula, then we will go with it, but how do we write it? If we check for any structural diagram, the formula we can write it like this. The formula is Z is equal to, here it is written, Z is equal to P1 in bracket x1 into P2 in bracket x2 into P3 in bracket x3 and so on. So it goes up to Pn into xn. Now in this we will check it, what is meaning of this Z. Now the thing is, here Z is the number of steps. Next, what we have it, P value. Now P is the number of speed steps in transmission group, and X is the characteristics of the transmission group or the number of steps in the spindle RPM. Just remember this formula. Now in case of a standard gearbox, how would you determine these values? First one, in case of a standard gearbox, we always try to keep x1 is equal to 1. Now what is the meaning of x2? x2 is always equal to p1, and x3, it is the multiplication of p1 plus p2, p1 and p2. Now similarly, if we calculate for x4, it will be p1 into multiplied by p2 into multiplied by p3. So similarly, this will go on. Now this is regarding structural diagram or structural formula, but we haven't seen what is the meaning of a structural diagram. Now if we have any gearbox which has 3 shafts in it, or it is a 3-stage gearbox, now in this we have a structural diagram which looks like this, and it is represented in this term. That is, 2 is our P1, 1 is our X1, 3 is our P2, 2 is our X2, 2 is our P3, and 6 is our X3. Now this is the thing. Now in this, how do we draw this structural diagram? Now first we will have to check for number of shafts in it. Now it will be given number of shafts, number of stages, like that, and as per that we'll draw number of lines in it. Now here total we have drawn 4 shafts. Now here it is 1, 1, 2, 3 and 4. After drawing these lines, next is the first one P1, it is this 2 in bracket 1. Now this 2 part, it shows that there should be a 2 line, and 1 indicates that there should be one common point for these 2 lines. Also it should be the distance of 1 unit between these 2 lines. Now if we'll check it here we have 2 lines. This is line number 1, this is line number 2, and in between these 2 lines there is a distance of 1. Okay, now where to locate these points? If we check for it, now here we have speed steps. Now here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if we count it, this is 1, 2, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 speed steps, and if we take midpoint of it, it will be 7.5 somewhere. Now here we have taken 7.5. Sorry, it is 12, 5.5 something, 6 actually. Now here we have taken midpoint of it. So after that, after taking a midpoint of it, we have drawn 2 lines. Here we have drawn 2 lines at a distance of 1. Similarly, if we'll go with 3 in bracket 2, so similarly what it shows? It shows that there should be 3 lines from the 2 points. So here we have 2 points, point number 1, point number 2. So there are 2 points here, and from each point there should be 3 lines. So there is, suppose here we are going to take point 1. So this is point first, this is second, and this is third. The thing is, it is already mentioned that there should be distance of 2 between each line. So there is a distance of 2 between each line. So if we check this line A1, so this is 1 distance, this is 2. Again from this point, this is 1 distance, this is 2. So like that we have drawn each and everything. Now these are all structural diagrams, so you will see each and everything in detail again while solving a numerical. So this is just an introductory part. Now these are the variations of it. Next is a ray diagram. So whatever we have drawn with the structural diagram, the ray diagram is exactly similar, but the thing is, while drawing ray diagram, we take only the lower or the minimum lines. Now in case of structural diagram, we have all the lines, but while drawing in the ray diagram, we take minimum lines. Minimum lines means what? Minimum value, the lines which has minimum value. So that is the ray diagram. Next we have speed chart. Now as we will finish with the ray diagram, we can easily draw with the speed chart. Now what it shows, in case of a speed chart, it shows you the total number of speeds. Now in this example there were 12 speeds, so here we are describing about 12 speeds. So it starts with the 1 up to 12. So this is from lower to higher. So this describes speed chart. Next we have deviation chart. Now deviation chart, in case of a deviation chart, whatever we have deviation in terms of number of teeth, so here the deviation chart is drawn. Now the basic deviation chart, here we have a deviation, and this is our mean line or midline, and this is the lower limit, this is the upper limit. So in between that, with the number of gears, so this line will come whether it has a deviation or not. So that again, all these parts we are going to see it in numericals in detail with each and every step. So this is just an introduction one. Next, after that, the point is of layout of gearbox. Now after finishing all these things, structural diagram, ray diagram, speed chart, now we have a layout of a gearbox. Now what we do with this? Now in this we do some calculations, and with those calculations we check it that how we can fix the gears and how many number of gears should be there on each shaft. So as you can see it here, now here we have machine or a motor. Here input shaft is connected to motor, and from this input shaft you can see there is 1, 3 and 5, fifth gear is connected. Similarly there is 2, 4, 5, 2, 4, 6, 7, 9, 11 number of gears connected to second shaft, and for the last one 8, 12 and 12. So all these 12 gears, those are connected in a particular position on shaft number 1, 2 and 3, and at the end here we are getting output of it. So with this we can understand that how many gears can be fixed on each and every shaft and how we can optimize it. So thank you very much.